Again, continuing the lecture from today and reminding you that we said that some problems might actually specify the motion of a particle along some path, and that path equation, and of course the point on the path could be represented as a distance r from the origin operating through an angle theta. So an r theta pair would give us a point on the path. And we could then specify the shape of the path as r is equal to some function of theta. We already had you think about and imagine in class what the shape of a path r equal theta would look like, and we decided that that would look like a spiral. So in an awful lot of common problems, we're given r is equal to some function of theta. We are also given, say, the values of the theta and its derivatives, theta, theta dot, and theta double dot. But to continue the problem, to get velocities and accelerations, we're going to need r dot, and r double dot, time derivatives of this r variable. But we're not given r as a function of time, we're given r as a function of theta. So we need to learn how to take those derivatives. So let's say we're given some y is equal to cosine of theta, and we admit that theta must be a variable that changes with time. How do we get the time derivative y as dy dt? Okay. First of all, we could do a geometry derivative, dy d theta. That's quite easy. If y is the cosine of theta, dy d theta is minus sine of theta. That is not the time derivative. This is not y dot. This is not dy dt. But we can get dy dt using this because we can write dy dt as dy d theta dt. That's a true statement. We have already computed dy d theta. That would be the minus sine of theta. Then we need to simply multiply by d theta dt. So dy dt is dy d theta, this piece, multiplied by theta dot. Likewise, what if y is equal to 4 times theta? Now, this one is very easy. We could use this chain rule idea from up here, but if we just have theta sitting there, we know that the derivative of theta is theta dot. And so we can simply say that y dot is 4 theta dot when y is 4 theta. But we also can follow the chain rule process, which says y dot is dy dt by definition, is dy d theta dt. What is dy d theta when y is equal to 4 theta? It's just a 4. So from this term we get a 4, from this term we get the theta dot, and so we get the answer is 4 theta dot. Either way works, the short way or the chain rule way. Looking at another piece, what if y is equal to the sine of theta squared? Well, we're going to need to, that's a little more sophisticated space derivative. We will say that y dot is dy dt, but that can be written as dy d theta dt. And the derivative of the sine of theta squared with respect to theta is going to be the cosine of theta squared times 2 theta. So cosine theta squared multiplying by 2 theta. This thing in parentheses is dy d theta, but we still have to multiply by d theta dt, which is theta dot, to finish out that derivative. Let's look at doing two derivatives. What if y is equal to 100 over theta? Then y dot is the derivative of 100 over theta with respect to theta, that's the dy d theta, multiplied by the d theta dt piece. And the derivative of 100 over theta is going to be, and so this is 100 times theta to the minus 1. So this will become 100 times, times minus 1 times theta to the minus 2. 100 times minus 1 multiplying theta to the minus 2. This piece is dr d theta, or dy d theta. There's the theta dot piece that drops down from our chain rule. This is now our first derivative. What if we want to go to a second derivative? Well, first of all, we have two pieces that involve theta, and two pieces, therefore, that change with time. And so we're going to need to take derivatives of both terms using the product rule. And the product rule will say take the derivative of the first piece with respect to time and multiply by the second piece. Then take the derivative of the second piece with respect to time, multiplying by the first piece. We will do that. So if our y dot, dropping straight down from above, is this, then y double dot is going to be derivative of this first piece with respect to time. But we're going to do that in two pieces because we're going to take a derivative with respect to theta and then multiply by theta dot. The derivative of minus 100 over theta squared, the derivative of that with respect to theta is going to be and so this is minus 100 theta to the minus 2. That's the way I usually think about that. And so this is going to be written as minus 2 times minus 100 times theta to the minus 3 power would be the derivative of this one with respect to theta. So that's going to be a positive 200 divided by theta cubed. So positive 200 divided by theta cubed right here came out of d y dot d theta. But now, to finish up the derivative of this piece, I've got to multiply by the d theta dt piece. That's a theta dot. But I already had another theta dot sitting right there. It just dropped straight down. And so I've got two theta dots being multiplied by together. So my first term is positive 200 over theta cubed times theta dot squared. That's the first term out of the product rule, taking the derivative of this piece while holding that piece constant. Now I'm going to take the derivative of that piece, which is very easy. That just becomes theta double dot times the minus 100 over theta squared. Theta double dot times the minus 100 over theta squared. These two terms give us y double dot. Okay, so we've taken two derivatives of a function of theta. Let's look at a problem out of the textbook that then puts that to work. So a particle travels around a lightus. I don't know that term, but apparently it's this particular shape. It might be interesting to go find that shape. Defined by the equation r squared theta equal a squared. So that's the path shape where a is a constant. Determine the particle's radial and transverse components of velocity and acceleration as a function of theta and its time derivatives. Now what this means is we'll pretend that theta and the time derivatives are known. Now we're asked for the two components of velocity and we're asked for the two components of acceleration. Go to the equation sheet and learn how to deal with this. Here is our position r. Here is r dot. And I will zoom in a bit for a moment. And so we see that the velocity, r dot, has an ER piece and an E theta piece. So here is the radial piece and the transverse piece. We also notice that the acceleration, r double dot, has a radial piece made up of two terms and a theta direction, or a transverse piece, made up of two terms. So in order to write these as functions of theta and derivatives, notice they already involve theta and their derivatives. But we're going to have to write r dot as a function of theta and its derivatives. And we're going to have to write r double dot as a function of theta and its derivatives. So we've got to take those two derivatives. Here we go. Let me zoom out. Okay, so we were given our geometry as r squared theta equals a squared. Let's turn that into the form r is equal to a function of theta. So r is equal to a theta to the minus 1/2 power when we do the algebra to isolate r. Okay, now we want to go to r dot. This is the author's solution enlarged, and there's a few mistakes in the author's solution, so I'm going to fix them. R dot is equal to the derivative of this thing with respect to theta times d theta dt. This quantity right here, all the way out to the minus 3/2 is dr d theta, and this piece theta dot is the d theta dt piece. So how do we take the derivative of a theta to the minus 1/2? That's going to be a times minus 1/2 times theta to the minus 3/2. A times minus 1/2 times theta raised to the minus 3/2 power. Okay, that gives us r dot, and if we know theta, dot, then we could compute a numerical value for r dot if we wished. Now we need to go one derivative higher to r double dot. We will take the derivative of r dot with respect to time. Notice I have a theta and a theta dot piece in here. Both theta and theta dot may quite well change with time. So I've got two terms multiplied together that change with time. So I've got to use the product rule to deal with this, and I'm going to use the chain rule to deal with the derivative of this. And so product rule says I'll take the derivative of this while holding that constant. Then I'll take the derivative of the second one while holding the first one constant. And so my r double dot is going to be two pieces. Now notice a times minus 1/2 is going to appear in every term. So let's just bring that piece out. A times minus 1/2. Then we're left with taking the derivative of theta to the minus 3/2 multiplied by theta dot. The derivative of theta to the minus 3/2, which would be a drd theta piece, is going to be minus 3/2 theta to the minus 5/2. Minus 3/2 theta. This should be theta to the minus 5/2. The author got that wrong and put a 3 there. So that's a theta to the minus 5/2. Okay. The derivative of this piece with respect to time is minus 3/2 theta to the minus 5/2 multiplied by theta dot, drd theta, d theta dt. But we already had a theta dot sitting there, so that's going to give us two of them. That means we're going to get a theta dot squared here. Then finally, we'll hold this piece constant and take the derivative of the theta dot piece, which is the theta double dot. So this will become theta to the minus 3/2 theta double dot. Theta to the minus 3/2 theta double dot. Notice we now have the constant and we have terms involving theta and its derivatives. If we knew numerical values for theta and its derivatives, we could calculate a numerical value for r double dot. Now we have, in theory, theta, theta dot, and theta double dot, because we said we would presume we know those. And now we know r dot, and r double dot in terms of these, which means if we had numerical values for these, we could crunch numerical values for those, which means we could go to the equation sheet and crunch numerical values for all of the velocity and acceleration terms. But instead what we're going to do is we're going to replace right here r dot. We'll replace that with the r dot as a function of thetas that we just solved for. We'll place r as a function of thetas. R double dot we have written as function of theta and its derivative. We'll substitute that in here. So we'll have four different terms where we'll make those substitutions. The radial piece of the velocity term was just r dot. And so we will grab the r dot equation right here. And there is our r dot piece. The velocity component into theta or transverse direction was r times theta dot. We'll grab r from our early effort, write it down that way, and multiply by the theta dot that's sitting right here. This is the transverse piece of velocity. The total velocity is a vector composed of this in the radial direction and this in the transverse direction. Now, our two pieces of acceleration, straight from the equation sheet. Here's the radial piece of acceleration, but we're going to write this using the r derivatives that we just came up with. And so r double dot will be this thing written as two pieces. So all of this is r double dot correcting that one to become a 5. So that takes care of this term. This term is r times theta dot squared, but we will write r as we did earlier, a theta to the minus 1/2, a theta to the minus 1/2 times the theta dot squared. with a minus sign in front of it. This gives us our A sub AR piece. If we want to, we could do just a little bit of algebraic simplification on this thing. It still doesn't simplify too much, but we have the radial component of acceleration involving theta, theta dot, and theta double dot. Now the transverse piece of acceleration coming from the equation sheet is the R alpha piece plus the Coriolis piece, and we'll substitute R to involve theta, and we'll substitute R to involve theta. This one's a little bit easier. So R as a function of theta is right there. So here is R theta double dot, and then 2R theta dot is going to be involve 2 and let's see, 2 and R. I remember what it is. Okay, author's mistake. 2 R dot theta dot. Check the equation sheet. 2 R dot theta dot. And so this quantity is R dot copied from above. Here's the R dot piece. And multiplying by theta dot, there's that theta dot. And of course these two theta dots combine into a theta dot squared. And we can do a little bit of algebraic simplification on this to come down to this, but we have a function that the transverse piece of acceleration from the R alpha and the Coriolis term will be a function of theta, theta dot, and theta double dot. Now, if we knew numerical values for all of the theta pieces, then we'd have numerical values for all of the velocity and acceleration pieces, and then we could compute further. And maybe in chapter 13, we could calculate some acceleration pieces, or from the acceleration pieces, we might calculate forces. That would be the end of this example.